as I was mentioning and using the comparison test in lecture A here, I am switching around the roles of AK and DK in this divergent example. It doesn't matter what you call AK and DK as long as the idea is right. Okay, in this case, the idea is that you want the terms for the series you want to prove divergence for to be bigger than the terms of the series that you know diverges. I want to get into something called the limit comparison test in a few minutes, but I also want to remind you to look for geometric series examples. So again, a geometric series, we're typically writing like this. And if it's an infinite series, put an infinity up there. It would look like this, going on forever. And we're actually going to see, when we talk about power series and Taylor series, that it'll be fruitful to think about x as actually being a variable here. We'll create a function of x. Remember that the corresponding sequence of partial sums for this has a nice formula. And it really is a formula you should try to remember. Okay? Again, you can use a note card, but it's worth remembering this formula so you can use it as quick as you can with these things. It looks like this as long as x is not equal to 1. If x equals 1, then it's actually simpler. It's actually a times n if x equals 1. But let's just not even worry about the x equals 1 case. That's the partial sums. What's the limit of the partial sums as n goes to infinity? Well, it depends on what x is. And if x is between -1 and 1, this is going to go to 0 and the whole thing will converge. If not, if x is not strictly between -1 and 1, then you get divergence. Think about it. I mean, like if x was, say, 1/2. 1/2 of the first is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. It keeps getting closer to 0. And that in general will happen if x is between -1 and 1. This is something to just know. X to the n goes to 0 as n goes to infinity if x is between -1 and 1. So Sn goes to a times 1 minus 0 over 1 minus x, which is just a over 1 minus x. If x is between -1 and 1, you get convergence in that case. This condition is often written that the absolute value of x is less than 1 as well, so you should be aware of that. All right? Let's do a quick example. And I can pick a to be anything that I want, and x anything I want as long as it's between -1 and 1 to get convergence. For example, I could pick a to be 17 and x to be -2/3. There. The answer is supposed to be a over 1 minus x. This x is between -1 and 1, it's -2/3. What's a over 1 minus x? It would be 17 over 1 minus -2/3. Which would be 17 over 5/3, which would be 17 times 3/5, which would be 51/5 is the answer, 10.2. Let's see if we get that. Yep, 51/5. Okay, so geometric series don't go away. They still continue being really important. Right, so we're always going to be thinking about geometric series pretty much in 9 and 10 a lot. Don't forget about it. This comparison test stuff is pretty tricky, and I'm having you do with things as proofs. There's another test called the limit comparison test, which is a little less tricky in some circumstances especially, and can be used to prove convergence or divergence as well. When you do the problems using this limit comparison test, I do want you to do them as proofs as well. So the two kinds of proofs I want you to do for the comparison test and the limit comparison test. Let me modify this problem a little bit that we just did in lecture, at the end of lecture A. Let me make it a plus sign down there instead of a minus sign. Plus sign here now. Does this converge or diverge? The intuition is the same. This still acts like k squared in the bottom when k is big. So k over k squared plus 1 still acts like 1 over k when k is large. So because of that, you would think this diverges. However, if you try to use the comparison test, you run into a snag in that this inequality is no longer true. Because I made the bottom bigger, the fraction has become smaller, not bigger. It's no longer true. I can't say that. So I can't use the comparison test. But I can use the limit comparison test. Again, I'm not going to write down the statement. If you've got your book, you can look at it on page 514. In using that test, you should verify that your terms, the AK and the BK, are positive. You can see that as a condition in the test. Note that AK is positive and BK is positive for all k greater than or equal to 1. I did make AK the new example here now with a plus sign instead of a minus sign. I'm going to keep that plus sign there. What else do you need to do to use the limit comparison test? You need to calculate a limit and show that that limit exists and is positive. What is a limit of? It's a limit of the ratios of the A's and B's. Can you see that? Looking at page 514 right in the middle there. Again, I'm using K's instead of N's. It doesn't matter. Does the limit as k goes to infinity of AK divided by BK exists, first of all? It's not infinity or something. And is it positive? If it exists and is positive, then the divergence of the harmonic series will imply the divergence of the series we're interested in. I'm leaving these sentences here essentially unchanged, except I should add the word limit in here. Because that's what I'm hoping to conclude by the limit comparison test, page 514. But I got to calculate this limit here. Zoom in maybe if necessary here. What is the limit of this ratio? Well, what are AK and BK? It's this divided by that, which is the same thing as this times the reciprocal of that. Is it okay if I skip a step? I'm doing this divided by this, which is the same as this times k, the reciprocal of this. So it really becomes k squared over k squared plus a half. I skipped an algebra step. And that is a rational function of k, where the numerator and denominator have the same degree. And you know from back in Calc 1 and maybe even pre-Calc that the limit of such a thing as k goes to infinity is the ratio of the coefficients of the highest power, which are 1 and 1. This limit is 1 divided by 1 is 1, which does exist, that is not infinity, and it is positive. It's important that it's positive and not 0. Therefore, since we know this series diverges, the limit comparison test now implies that our original series diverges as well. So, pretty similar structure to the proof with the regular comparison test. Just some of the intermediate details that are different. You need to verify that the theorem can be used before you use it. If You verify the conditions in the theorem, in this case, that these are positive, and that limit is positive, and then you can use the theorem. In this case, again, the limit comparison test. Okay, and that's easier to do than the comparison test here because, again, this is not greater than or equal to that. It might be greater than or equal to something else whose series converges, but what that something else might be is not clear. And again, don't forget to put your summation signs down here. They must be there for full credit. I'll tell the graders to look for those too. All right, what else? Absolute convergence, ratio test, and alternating series test. Actually, let's focus on the last two, and if we have time, we'll look at the absolute convergence. That's the ratio test. It is another test to see whether a series might converge or not. It can be used, unlike the comparison tests, this one can be used even when some of your terms are negative. With the limit comparison test and in fact the ratio test, the terms have to be positive. Actually, they don't have to always be positive. They can just be eventually positive after some point, and that's good enough. It doesn't have to be true for all k greater than or equal to 1. It could be true for all k greater than or equal to 20. And that's good enough. But the ratio test will apply to any series whose terms are either positive or negative. Though it is a little tricky sometimes if some of your terms are 0, you kind of want to ignore those terms because you're going to be calculating a limit of a ratio, and you don't want to divide by 0. Again, I could use a k. I'll use an n this time. Okay, it's okay to use a k or an n or whatever, it doesn't matter. Here's the limit that you calculate, if you can calculate it. The limit of that ratio, that's why it's called the ratio test. Again, I'm not going to state the theorem in terms of writing it down on the board, but let me just say it verbally here. You can look at the book, it's on page 515. If this limit exists and is less than 1, then your series will converge. If it exists and is greater than 1, then your series will diverge. If this limit exists and equals 1, then the ratio test provides no information. You can't conclude it converges or diverges with the ratio test. You need something else. What if the limit doesn't exist? Well, there are actually cases when the limit doesn't exist where it still converges or still diverges. We're not going to get into situations where the limit doesn't exist. So that's the limit you calculate. I'm just verbally saying what to do. Let me apply it to an example. I'll go back to using k's here. It's commonly useful when your series involves terms that involve k as a power, or with a factorial involved. For example, here's a common example to think about with the ratio test. Add up 2 to the k over k factorial. Have you seen factorials before? You should have. When you say 5? No. Say 5 factorial. It means 5 times 4 times 3 times 2 times 1, which is 120. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1, which is 720. 2 factorial is 2 times 1, which is 2. 1 factorial is just 1, which is 1. Actually, you can define 0 factorial as well. It's not 0, it's defined to be 1. Why is it 1? Well, in a nutshell, it makes formulas work out more nicely if you define 0 factorial to be 1. And that's a good enough reason to define it. It's not a deep fact, it's just a definition that makes formulas work out more nicely. We define 0 factorial to be 1. Here's AK. Let me go ahead and put absolute value signs in here, though they're not really necessary with this example. And I guess I'll switch to n here. Because these terms are positive, I will keep the absolute value signs there in the first step to remind you that in general they should be there. But in the next step I will get rid of them because I have positive terms here. Dividing by this fraction is the same as multiplying by its reciprocal. That looks pretty nasty, but it's actually pretty nice. 2 to the n plus 1 is the same as 2 to the n times 2. So the 2 to the n's cancel. Zoom in if you need doing that. There's a 2 to the n times 2. N plus 1 factorial, I hope you see, is the same as n plus 1 times n factorial. Right? Because, for example, 5 factorial is 5 times 4 factorial. So the n factorials cancel as well. And you are left with the limit as n goes to infinity of 2 over n plus 1 is what it simplifies to. And that limit is clearly 0, less than 1. Therefore, this series converges. Which is not obvious at first. I mean, 2 to the k grows really fast. K factorial grows really fast. The ratio can be seen to go to 0, so you can't use the divergence test. We've got to use something else. The ratio test verifies that this ratio approaches a limit less than 1, therefore the series converges. By the way, then, if I had switched the fraction around, if I had a k factorial divided by 2 to the k, that would be a limit where you'd get infinity here, and this would diverge. And in fact, it diverges by the divergence test as well if I switch those around. I'm talking about this one here. That would diverge either by the ratio test or by the divergence test. These terms you can check, not prove, but you can check they don't go to 0. As k goes to infinity. So that's the ratio test. And a basic example. You'll have some examples on the homework. More tests. Alternating series tests. I should mention before I write down an example with the alternating series test that the ratio test ends up providing no information for p series. Again, here's p series. And again, it's only interesting when p is positive. If you apply the ratio test to that, no matter what positive p you pick, you'll get 1 for the limit of the ratio test. And so the ratio test provides no information. But it does converge when p is bigger than 1 and diverge when p is less than 1. So there's a common example to think about where the ratio test provides no information. What is this alternating series test now? Let's think about it in the context of an example. And the example I'm going to write down is a famous one. There are famous examples in math, this being one of them. If you write this out without a summation symbol, when k is 1, you get a 0th power here. Negative 1 to the 0 is positive 1 times 1 is 1. When k is 2, you get negative 1 to the first power, which is negative 1, times 1/2. You get a minus 1/2. When k is 3, you get a second power there. Negative 1 squared is positive 1, times 1/3 is positive 1/3. When k is 4, this is a third power there. You get negative 1 times a fourth is negative 1/4. Etc. Then you get plus 1/5, minus 1/6, etc. If these were all plus signs, that would be the harmonic series, and it would diverge. But they're not all plus signs. They alternate plus, minus, plus, minus, plus, minus, plus, minus, etc. They could also alternate the other way, minus, plus, minus, plus, minus, plus. I could make this power a kth power instead of a k minus first power. In such a situation, where the series alternates in sign, and where the things that are getting multiplied by the -1 to the k minus first power in this case, where these things form a sequence that decreases to 0, that's a situation for the alternating series test, which you can look at on page 517. A series of this form. This thing that I circled in black here is a sequence of positive things that decrease to 0. The alternating series test on page 517 guarantees that this series does converge. It's a situation where you can apply the test. However, I should also say that its convergence is kind of fragile. It's a fragile kind of convergence. What do I mean by that? I mean, if you decide you want to try to break the convergence of the series, it can be done. How? Just by rearranging the terms, actually. You can cause it to either converge to something else or cause it to diverge by rearranging the terms appropriately. That doesn't sound like a good thing. It is a fragile kind of convergence. It's sometimes called conditional convergence, sometimes also called non-absolute convergence. And that'll happen whenever the corresponding series with all plus signs diverges. The convergence you get for this kind of thing will be fragile in that sense. You got to be really careful with infinite series. Let me end class by showing you, I think I'm not going to talk about absolute convergence here, although I sort of did already. Let me show you something weird that can come about if you're not careful with infinite series. 0 does equal, I hope you would agree, 0 plus 0 plus 0 plus 0 plus 0, etc. forever. Hope nobody argues with that. And 0, I hope everybody agrees, is the same as 1 minus 1. So this is the same as 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 forever and ever. And by the associative property, this is the same as 1 plus -1 plus 1 plus -1 plus 1 plus -1 plus 1 plus -1 plus 1 forever, which I hope you would agree is the same as 1 plus 0 plus 0 plus 0 plus 0 forever, which is 1. Have I proved 0 equals 1? It can't be true. There must be a problem somewhere. Where do you think the problem is? Which equality here? First, second, third, fourth, or fifth? The third one's the most fishy, and that indeed is the problem. You can't do that with this series. You can do it with some series, but not every kind of series. This is, in a sense, a fragile series here, so to speak. And you can't do that. You can't. The associative property doesn't work with this one. Okay? So, weird things can happen with series if you're not careful. We do want to endeavor to be careful in here to a certain degree. All right, finish early for you guys a little bit. I didn't quite finish early for the other class. Have a good day.